So we've seen that we can only use that new inverse function notation that's got the little -1 between the f and the x part when the original function and its inverse are both functions. But what can we do if we've got a function and its inverse isn't a function but we want it to be? Well, we can actually just restrict the domain of the original function so that its inverse is a function. How do we do it? Well, there's always more than one way. And to decide, we really just need to make a sensible choice. Looking at a graph of the original function will help you. And that choice should either maximize the domain of the inverse function or perhaps just suit your purpose. Maybe you've got time on the x-axis and you only want positive values of x. So let your application decide which section of the graph you might prefer to use. So a simple example here, we've got the function y equals x squared, which we can write like this, and we know it's just our basic upright parabola. We know that when we find its inverse, we're going to get a parabola on its side like this, and it's going to fail the vertical line test, so it's not a function. We can also see that if it's going to fail the vertical line test, it's because the original function failed a horizontal line test. So what we can do then is look at the original function graph, this helps us, and spot any places that it's going to fail that horizontal line test and eliminate those places. Now this one's nice and simple. I can see that it really is just made up of two kind of arms, I guess. And so basically I really just want the right hand arm or the left hand arm, and I can't have both. So the natural choices are that I could let x be greater than or equal to 0 and just have this part, or I could let x be less than or equal to 0 and have that part. Which am I going to choose? Well, I'll go with the positive numbers, keep it simple. So then my first step is to rewrite this as y equals x squared, but to put my restriction in now and say x has to be greater than or equal to 0. Then I can switch my x's and y's around to make the inverse, but I have to switch them in the restriction as well. Then I can rewrite this getting y as the subject and say let's take the square root of y squared, that would give us y, and we want the square root of x. Now often you'll put in there naturally just plus and minus the square root of x. We don't want that, because remember what we really want here is we want y to be greater than or equal to 0. Now why did I not have that written in the first place? Well, the square root of x by definition is positive. So if the right hand side is positive here, the left hand side will also be positive. And so if y is already positive here, I don't really need to reiterate that. I mean, I could write it, it's not wrong, but it's also not really necessary. At this point I can say, right, I've got it in that form y equals something, so I can now write it using my new inverse function notation and say the inverse function of x is the square root of x. And that is going to look like just the upper arm of that sideways parabola, which we've already seen. Now, if I was to make a different choice and say that x had to be less than or equal to 0, then I would be saying that x had to be less than or equal to 0 here, so y would have to be negative as well. And that means that when I got into here, I would need to have put a negative sign in there and also in here. And that would have given me not the upper arm, but the lower arm that's going to sit down there like that. This second example is a little bit different because once we've made our inverse, it's very hard to get it in the form y equals something. So we can't use that inverse function notation that we've learnt today. But we can still create a function that is restricted so that its inverse is also a function, and we can come up with a formula for it. So we can see that this is a cubic curve. It's got a normal x-intercept at x equals 1, and it's got a double root when x equals -1, and so that means it just touches the x-axis there. Now, if we're looking for what will happen when we find the inverse of this, we can see that anywhere that the original function fails the horizontal line test, its inverse will fail the vertical line test. So looking for problem points, we can see that if we just take anything from here all the way up, that will pass a horizontal line test just fine. And anywhere from here down will also pass a horizontal line test just fine. It's this part in here that's the actual problem area. So it's the bit that we don't want. So what do? Well, we could have x being less than or equal to -1, or we could have x being greater than or equal to 0. I'm going to take that option because it looks like the more straightforward one. So then I can just write out my function again, subbing in y instead of f of x. So I've got y equals x minus 1, x plus 1 squared, but I've also got my restriction in now, which says that x has to be greater than or equal to 0. And that effectively means I no longer have this part of the graph. It's gone. Okay, now I can swap all my x's for y's, including swapping them in the restriction. And I can pretty well just stop there and say, look, this is actually now going to be a function. And it's not in the form y equals something, but it's hard to get it in that form. So this is kind of a good place to stop, I suppose. It does define the new inverse function, and it does clearly show what the restrictions need to be. Now, what's this going to look like? Well, imagine where our line is, y equals x. It's going to be a reflection around that line, so it's going to look something like this and head off in that direction. Okay, that curve isn't great, but you get the idea there. So when it comes to drawing them, use that idea of reflecting around the line y equals x, and your formula may or may not be able to get into this form, but we can see a workaround for even when it can't.